So the topic is a bit shifting towards molecular systems. I'd like to talk about the interaction of electronic properties or the interference with vibrational properties, and this naturally connects to electron vibrational coupling and polarons. So let me, since this is the first talk maybe dedicated to these new classes of materials, introduce a couple of those. So we are concerned, for instance, with those molecular crystals. So these are simply stacked molecules, small molecules, stacked on top of each other, mainly bonded by weak van der Waals interactions in a very well-ordered way. But you can also have more disordered systems like these blends. So these are mixtures of different type of molecules, acceptor type and donor type of molecules. And this is obviously more related to organic solar cells and functionality, optoelectronic functionality. And you have polymers where the bonds basically are both basically can have covalent bonds between the different monomers, but those polymer chains stack on top of each other, and basically there is weak van der Waals interactions or weak hydrogen bonds present. So what they all share is that they are strongly dominated by their vibrational properties. And if you compare, for instance, the energy scale of typical electronic features, like if you consider, for instance, the electronic coupling between the different monomers, between the different units, this can reach 100 milli-electron volts or a couple of 100 milli-electron volts, and this is the exact same energy scale of electron-phonon coupling. So this is a strong effect and very relevant effect in these molecular systems. Just to give you a bit of idea how electron-phonon coupling manifests, so one possibility to view that is essentially to look to such trajectories and look for the electronic properties as a function of time, and you will see, you can understand, imagine that, for instance, the ionization energy of this poor guy here in the middle that gets beaten up is changing over time, so the geometry couples to the electronic properties, for instance, to the electron affinity or ionization energy. So another perspective you can have when looking to single molecules and look to the charging of those molecules. For instance, this guy gets charged, so this is a cationic form, while this upwards band side groups is the neutral form. So upon charging these molecules, they you put them basically under quite some stress, and this stress can be released by this relaxation, and this is called the relaxation energy, and can amount basically up to an electron volt. So this is really a big energy scale. So electron-phonon coupling and polaric effects are very important in these systems, and give rise basically to the coupled and tangled dynamics of electrons and vibrations. From theory, this is usually described by this kind of Hamiltonians, Holstein or Holstein-Piles Hamiltonians, where essentially the coupling is between the electronic degrees of freedom, and here we have the coupling constants in a slightly different definition as compared to the previous talk. So those are the dimensionless coupling constants in this case, because you take out the vibrational frequency. So the sum goes over all the vibrations, and we can have many of those in these systems. So now what is the effect of electron vibrational coupling? So if you take a very simple model system like a tight binding chain, so imagine you have a stack of molecules and they're coupled just by a nearest neighbor interaction, then you can easily derive this cosine type band structure. So this is without vibrational coupling, but if you turn on electron-phonon coupling, even if it's not very large, you get this spectral function. So that looks quite different. You have different effects. For instance, we have what we call band narrowing, so an increase of the polaron mass compared to the previous speakers, and you have an additional replica feature of the vibrations. So obviously, this is a non-perturbative regime that needs to be treated correctly. We've been looking into that from the transport point of view some time ago, and could work out an analytical, so approximate approach to calculate carrier mobilities in these crystals, where you can take into account this polaron dressing and scattering, and improved quite significantly the previous approaches, and at least could show that those effects like the temperature dependence of the mobility can be reproduced as compared to the experiment. So there were quite some improvements at that point, but still there's some way to go. So open questions are, do all the vibrational modes behave like that? So there we're coming back to the question of the time scale that was asked previously. How about fast and slow modes? Do they all dress the electron when moving throughout this system? And the answer to this question will be no. And the second question is, how about disorder? If we really put those systems under disorder, so how is polaron formation happening, and how is polaron transport happening? So focusing on the second question, we looked into that, and this is an approach that we followed essentially based on the Kubo formalism, where we calculate the carrier conductivity from these simulations, these time-dependent wave packet simulations. So this is just a movie to illustrate what's happening. So you measure the size, essentially, of these wave packets as a function of time that is directly related to the conductivity just by the derivative, so the time derivative. So you look to the expansion, and then you see, for instance, a scattering or multiple scattering of those wave packets. And with this, you can essentially access all these transport regimes as a function of time. So you have the ballistic regime for very small times. You can have diffusive transport regimes or localization if there is a lot of disorder in the system. So you can study the impact of disorder, and this simple approach can be applied to 3D systems, for instance. So that was just a very simple model system, 3D model system with one vibrational mode. And as a result of putting disorder, you indeed have a departure of this mobility saturation at low temperature, and you see that once you put some disorder, then the mobility goes down, so you have indeed some localization of those quasi-particles that are now polarons. And still there's the question of how these low-frequency vibrations really act in this system, and what is the difference to the high-frequency vibrations. We looked into that in the context of charge transfer absorption. So here we slightly change to polaric excitons. I think it's not a real problem for you. What you see is actually it's an absorption spectrum here versus energy. And the system is like this disordered system. And what we are looking at actually is to those low energy absorption features, which are the CT states. So from the donor to the acceptor, so the charge transfer exciton. And what is interesting here is to look to the line width of these features, because there can be signatures of electron-phonon coupling of this interaction that we wanted to extract. So we compared actually those experiments to simulations. What we did is we fit this Gaussian with the standard, if you want, the Marcus kind of approach. And we compared that to the simulations from theory. So here you have basically the width of this Gaussian line shape. The width is related to the relaxation energy. At least that is the hypothesis here. Of course, you can always have disorder, and that gives you broader features. So we wanted to see if this simple, purely electron-phonon-mediated bandwidth model works, and we compared that. So here you see the theoretical calculated relaxation energy versus the experimentally obtained one from the fitting. And at first glance, you see that, well, that looks quite, say, correlated. You see that if you calculate the molecular relaxation energy of the donor, and if we add the C60 value as the acceptor, there's an offset, you find that there is quite some agreement between experiment and theory. So that looks quite promising at first glance, as I said, but we were wondering actually because there's some inconsistency, because you may wonder how can the bandwidth that you calculate in theory be larger as compared to the experimental one, where you can have additional broadening like inhomogeneous line width effects, for instance. So we looked into that a bit deeper and realized that, well, we didn't quite do that correctly, because what we have to do for the calculation of those relaxation energies, we have to essentially cut off these high-frequency modes, because they do not contribute to the line width. So here you see a couple of molecules with their homo orbitals, essentially. And when we look to the vibrational distribution of all these electron-phonon couplings, so what is here plotted is the accumulated relaxation energy. So each vibration contributes to this relaxation. If you think about the degrees of freedom, each degree of freedom in this molecule contributes a little bit to this total relaxation energy. And here you see there are molecules which are strongly dominated by low frequency modes, and there are molecules that are strongly dominated by high frequency modes. And that makes a strong difference because these high frequency modes do not lead to this line width effect. So we cutted them away, and we introduced basically with this cutoff so-called reduced relaxation energy. And if we now compare the simulations now to the experiment, you see that they are really just below that line. So this is really consistent, and a little bit broader features in experiments can be assigned to due to some, say, residual disorder, for instance. Okay, but this is very important because this gives you an insight which of the modes you have to treat in which way. Yeah? So which of the modes you have to treat in a full quantum mechanical way, and which of those modes, those low frequency modes, you have to treat or you can treat in a quasi-classical way. And this is very important for methodological developments. So one step in that direction we did just recently, again based on the Holstein Hamiltonian. So we have basically molecular crystals, not the most high mobile ones, and we were looking to a hopping approach, to a hopping transport regime. So imagine we have like a hole is sitting here and wants to go there. You have to, say, distort those molecules. And what is important is the time scale of this hopping event. And the time scale of this hopping event must be compared to the frequency or the time scale of the vibrations. So this is indicated in this plot here. So this is a typical hopping time. And you see that there are some of the vibrations that actually don't change at all on that time scale. So they are so slow that they are quasi-constant. And there are some of those modes that change quite rapidly, those high-frequency modes here in this region, for instance. And those high-frequency modes do change during this hopping time. And this makes a strong difference. And you see that there are many modes in those systems, and you have to distinguish the quasi-static from the dynamic modes in this treatment, because the static ones, they behave like a random disorder, and the dynamic ones can really assist transport. So this has been included in this what we call the time-consistent hopping approach, where essentially we calculate this hopping rate self-consistently, because this hopping time is not given, but actually depends in itself on this separation scheme. As I said, if the mode is essentially slow, then of course you feel a random disorder landscape, and it will impede the transfer of the charge from one side to the other side. But if it's a dynamic mode, then it can possibly enhance transport, and as a result of that, the hopping time that you calculate, or the hopping rate, really depends on this separation. At the same time, this needs to be treated self-consistently, so this rate in itself must be sufficient, basically exactly in between the this quasi-static and the dynamic modes. So you can demand, you can ask for this requirement and go through the self-consistency loop, and only then basically make this hopping happen. And if you do a kinetic Monte Carlo simulation, you can compare, and this is a plot that shows the statistics essentially of the actual hopping time that you calculate. So imagine you have a kinetic Monte Carlo run, and you calculate all the hopping times in your trajectory, and then you can compare that to the time-consistent hopping time. So the one that you take in your favorite hopping approach compared to the one that is calculated time-consistently, taking into account the separation of modes. And of course, for the time-consistent hopping approach, they are all at 1, so all the hopping rates that you calculate are time consistent. But if you compare other very popular hopping approaches like the Levy-Jortner one or the Marcus theory, you see actually that most of the hopping events are completely inconsistent. So the hopping times that you take in those are easily by a factor of 10 or a factor of 100 off. So they are completely nonsense. For instance, you calculate a hopping time that is a few that is very, very short, and you assume essentially that during this hopping time, all the modes have essentially evolved through a couple of periods, and this is not true, and that's why this is inconsistent. You see there is quite a strong distribution. The same is true for this Marcus theory. So I think this needs to be addressed in future approaches more in detail. I think with this coming to my acknowledgement slides, I would like to thank the co-workers, Sebastian, Michael is in the audience, Sebastian and Jana who contributed to that, and of course the funding agencies. And I would like to invite you actually next year to some nice workshop and symposium on electron phonon and Polaron and excitonic physics, and I hope to see many of you there and many submissions from your side. So thank you very much.
Okay. Questions?
Very nice talk. Follow up the point you make at the end. I mean, I agree with you. I've always been suspicious with Marcus rates, but there wasn't anything better. But
Maybe this is. So this is a hopping approach. So it in this version that we have compiled it now, it is not treating a coherent transport. So we analytically went to the limit where you have this hopping approach. But in principle, that would be the next step to take coherent motion into account. So in the sense, I wouldn't apply it right now to polymers because, I mean, even not for interchain transport, because, there are also subtleties that cannot be directly addressed by this. So this is like for systems where the hopping approach is very well justified, not so big transfer integral, so maybe not the naphthalene or pentacene material, and not the most high mobile materials where you can suspect strong coherent contributions and delocalization.
You just give me my last back. Thank you.
Could you show a kinetic equation of polaron mobility?
Oh, yeah. That was, yeah. Here we go.
Yes.
Yeah.
Is this here anything common with known kinetic equation approach for the polaron mobility of, for example, Froelich polaron, like Kadamov equation or something else?
So what has been done essentially is, again, this based on the Kubo formalism, and the analytical treatment essentially is based on the Lang-Filsov kind of treatment transformation, and you calculate essentially the current correlation function, which is being expressed in terms of the material parameters that you have in your Hamiltonian essentially. So you see that, for instance, you have the lattice vectors for the crystal. You have basically transfer integrals which are renormalized. So this is due to the Polaron renormalization. And so the physics continues. If you look, for instance, to the time integral, you have kind of energy conservation from the, say, initial state to some final state scattering, where also the occupation numbers from the initial state and the Pauli blocking enter. So all that... no. But that's a question for the future. Yeah.
I refer to crystalline organics without atoms. Even in this case,
Sorry.
like green, for example. Even in this case, you have the separation of energy scale between the sliding modes, for example, and the intramolecular modes. While in your treatment, just slightly with all the modes in the same way. In your last
development, yeah.
Modify your approach in order to take into account more the open regime. Do you think that this same approach would work also in this much more ordered case, in the case of crystalline organics? Or,
Well,
for example, you can have also localization which does not come necessarily from subtracting. You mentioned before
static disorder, yeah. Yes, so you can indeed go beyond this formula. So that is obtained after, say, making quite a sequence of steps of approximations, which, for instance, is that you basically kill all the coherences that go beyond one site. So that's why this I would not directly apply to Rubrine, but this can be extended, and I think this vibrational mode separation, independently of which transport mechanism you have at the end, this separation of vibrational modes is very important, I think, and for improving the quality of different approaches. I think this should be taken into account in the future. If this answers, we can maybe discuss in. Okay, good. Thank you.
This bit at the end, you've kind of made a temperature-dependent reorganization energy for Marcus theory, but Marcus theory is the classical high-temperature limit. If you go just one step back in the derivation, then you do something of an individual phonon modes or a Bose-Einstein distribution, so you get a freeze-out of modes for your high-frequency, low-frequency, I think, directly there. So, I mean, is this the necessary thing to do, or should we just, put a bit more effort into our calculations and not use Marcus theory?
I'm not fully sure if I got the question right. So the difference to the Marcus theory is essentially that you that this the smallest energy scale is a transfer integral, and that's the term that you treat perturbatively. But here we have basically modes that essentially can be significantly low energy, such that they are really giving rise to some say static disorder. So in Marcus theory, you have to usually make an ad hoc assumption whether or not your energetic landscape is static or not. So this is, since this is everything related to the vibrations, in principle you can look at that and look if this moves over the time scale of the hopping event, which is not treated in, which is not done in Marcus theory, because Marcus theory, the slowest time scale is the electron transfer at the end, and everything that moves has moved during this time scale and basically leads to the full reorganization energy. So that's why in Marcus theory you have the full relaxation energy here, and in the high temperature limit, actually, you get this quantity back. If I'm not misled, yes, I think you should get it back. Yeah.
Okay, so the key thing here is that it needs to be quasi-static.
Yeah. So the quasi-static is really this delta E. So this hopping energy difference from one to the other side that is due to the vibrations.